Morning. Okay, welcome back. New week. Still right now working through linear algebra kind of work. I think last time it seemed like some people were getting into revisiting linear regression. Others were kind of working on different things. But where are we at for today? Start off the week. Any questions or like interesting things going on? I know it takes a minute to like get set back up, especially Monday morning. I could check in and see where people are at, and then maybe come back up, see if demo would help kind of either explain or kind of show some common tripping points, anything like that. Yeah, this is like, I mean, this is finally on one dimensional. It's like stretching the version to this second. So crazy. What did you go do? Oh, okay. But I just do the yeah, you end up with exactly this is the equation that you get time elements. It's just more. Yeah. Yeah, and like so the dimensions are always the number of nodes that is So some things that were coming up as I was looking around, and this is and most of these things are things that, like, if you're dealing with linear algebra in a computer for the first time, it's hard to kind of make sense of these. So when we were looking at this problem, we were trying to come up with, like, what is, I know I know it's linear, so I know that it's something T1, T2, T3 equals something on the right hand side, but sometimes it's hard to figure out like what goes where. So at least the way that I kind of think of it is like every row is going to be my equation. This is equation 1, this is equation 2, this is equation 3. So as I'm looking at equation 1, 2, 3, that's what I'm trying to like transcribe into a matrix itself. Every column here is going to be something times T1, because that's my first like vector that I'm solving for. This one's going to be times that T2, and this is times that T3. And then over here, this is like my right hand side, equation 1. And then so the right hand side usually, I don't know, it depends on how you want to do it, but sometimes that's easier to figure out first because it's all the stuff that's not multiplied by something. So I know I've got a negative q in every step. Get rid of those if I'm trying to like check them off one by one. Then there's also this like Tn value, that negative mCp Tn. So I'll call that like m1 Cp T in, and I ran out of space, but it's there. And now everything else that's in the equation has like a T1, T2, or T3. The T3 is easy in the first equation because it doesn't exist, so I can plug in at 0. And now that T1 and T2, here I've got like a negative M2 dot and a positive M6. And I'll multiply this whole thing times Cp, just so I'll just keep track of the mass flow for each of these. So I did those two, and now I've got like a positive M2 in that for T1, a negative M3 and a negative M6. For T2, and then T3 is a positive M5. And then last one, also nice, I don't have to worry about T1. And then I have a positive M3 dot for T2, and then T3 has M4 and negative M4 and a negative M5. Kind of like that. And yeah, depending on how you want to do it, but sometimes it helps to just like write out the equations and then start checking off like, all right, what did I keep track of so far in this equation? So that was one thing that came up. Another one was kind of a weird error, and it took me a second to realize like what was going on. But it happens pretty often. So coming down, like down in here. So I want F to go like 100 to 1100, take steps of 10. So let's go like 1101. And then I know my B matrix is like F is that middle value here. But when I try to run this, it's going to tell me, oh wait, np.a range, there we go. It gives me really more of a, so if it's pink like this, it's a warning. And if I try to look at what is that B value, So whenever it gives you that pink value, it's telling you that it is a warning. So it did something, like it did deliver. It created this vector B, or sorry, an array, a one-dimensional array B. But it's kind of a strange way to set it up because there's a 0 and then another array and then another 0, rather than kind of what we had wanted was kind of like maybe one value at a time, like F0 or something. So if you're getting this like big pink box, like take a look at what the array is that you're creating, and sometimes that helps you figure out like, all right, is this what I want, or maybe I want to plug in one value of f at a time, like make a for loop or something. Like in this case, I would probably want to say like for fi in f and then I could say like 0 fi 0. So I'm just grabbing one value of that at a time. Now I can say that np linalg solve of a comma b and we'll say like p1 is an empty list to start. And then I end up with that solution that I was looking for, where I'm just plugging in like 100, 110, 120, all at one at a time. And then, all right, so then last other thing that was coming up was, as we're trying to load in some data, whenever I tell NumPy like, hey, take a look at this, load in that text, it tells me like, hey, I don't know what do you want me to do with this value of time? Like it doesn't match anything else. And it doesn't make a lot of sense because I haven't really looked at what the data looks like yet. But the main thing is that it's telling me that it can't convert those letters into a number, which makes sense. Like I don't know what number time the letters TIME would be. So this is my process for it. I always like take a look at what the raw text is inside of that file, like with a head command. You can also use like cat and tail. Like there's all these different ways of like looking at what's really in this file, like what's the text that's inside that file. So head works well because it just prints out those first 10 lines, and usually that's all I need to load in like a standard formatted file. And I can see like, all right, well, this information is helpful, but I don't need it for any of the data processing that I need to do. So I want to skip one row. So now I know, let's say I can skip rows of 1. So I'm going to skip that first row. And now it still tells me it doesn't know what to do with 0, comma. Like, well, I don't want you to load the commas in there. Like, I want you to ignore that. That's the thing separating my data. And the way to tell it that that's the separator is that the delimiter is a comma. And now now it loads up that data as like one NumPy array, where the first column is time, next column is stress. And I know time is in seconds and stress is megapascal. It's also good to know. So that's what I saw so far. Anything else come up as we were working through? Yeah.
I was having trouble trying to figure out how to do the rounding error thing for the Hilbert matrix.
Yeah, like how to get.
Yeah, how to get the I was looking through the readings.
Nice. Okay. Good place to start.
I don't know. I'm just too tired right now.
It might be. Yeah. It's been a long semester. Okay, so we're coming back up to Hilbert matrix, and this one it does come up in a lot of numerical methods problems where you start, like, especially if you're doing like polynomial fits, like high degree polynomial fits. Sometimes you end up with like a Hilbert matrix where it keeps getting, as you move it along the diagonal, it keeps getting smaller and smaller and smaller. So the inverse of the Hilbert is going to be really large because the Hilbert itself was magnitude roughly kind of small. So it's a real problem that comes up. First step is just making the Hilbert matrix. So we want to make sure that we can actually make it. There's two ways. You can either write your own function, like 1 over I plus j plus 1. It's a little different than the Wikipedia article, which is I plus j minus 1, but that's because we're in Python base 0 instead of like MATLAB or anything else at base 1. So let's just make sure this works first. Hilbert of 2. And I get 1 1/2, 1/3. And if I go Hilbert of 3, 1 1/2, 1/3, and then 1/4, 1/5. So it just keeps getting smaller as I move along. Those like cross diagonal. It's not the diagonal. It's like the other diagonal. Cool. So that one seems like it's working. And then getting the condition number of it is so it's just a linear, the linalg dot condition will give me a number. And if you ever want to sound like really smart, like you really know what's going on, ask people for the condition number when they're doing like linear algebra problems, because now it sounds like, oh wow, that person really knows their numerical methods if they're asking for the condition number. And it's a really easy way to check, like, is the problem easy to solve or is it hard to solve? So here, 500, pretty easy. That's an easy problem to like invert that matrix and get an answer. Versus Hilbert matrix of 30 by 30. Now it's 2 to the 18. This is a very hard problem to solve, and for a computer, it's basically impossible. Like, you can't even trust the results that you're getting from the computer. Like, that's a very large condition number. And the reason for that is, let's jump back into the reading for a second. I know you said you were already in the reading and it was giving you nothing, but jump back in and head all the way down. Like, roughly this is the limit to like how well a computer can solve a problem, is that delta x, where x is like the answer that I'm trying to get, the amount of error that I'm going to get in that vector is going to be always, it could be as much as the condition number times like how well I can store that matrix. And for the matrix, like the error that I can store a number in the computer, 10 to the negative 16, that's our floor of how well we can enter a number into the computer. Like even pi, once we get to that 16th digit of pi, there's nothing more, like it's not giving us any more information after that. So whenever your condition number is anywhere in 10 to the 16 or higher, now you're starting to get errors on the scale of 10 to the 18 minus 16. So like 10 to the 2 or 10 to the 1. Those are large errors for something that is just a linear problem. All right, so what do we do with that information? We just plug it into an equation. Oh wait, I skipped over it, sorry. So right now, if I know condition number is roughly 10 to the 18, error for that 30 by 30 is 10 to the 18 minus 16. Yeah, 100 for that one. And then versus that 3 by 3, we had like 500. So it's 5 times 10 to the 2. So an error, for the error, the 3 by 3, it's not 18, it's 2. So now we're talking errors of around 10 to the negative 14. And that's why I say like that condition number, bigger it is, the more error you can have. It's not that the error will be that number, but that's, you have to expect that it could be up to that number. But that's the main goal here in this exercise. Step 1, make the Hilbert matrix. Then step 2, find its condition number. And then the third part is whatever 10, if you take that condition number, put it on a log scale. If it's 10 to the 6th, then it's 6 minus 16, because 16 is like our, how well we can store numbers inside of an array. Nice, good throwback to where we first started off. And then, I guess, yeah, if you want to see like the fancy way of doing that. How many n's do we have? 1, 5, 10, 15, 20. 1, 5, 10, 15, 20. Make it fancy code style, like because I'm taking like throw that condition number into a log base 10 and then take the floor, because I don't really care if it's like if the log base 10 is 1.38, all I really need is like the 10 to the 1 rather than 10 to the 1.38 to get it back to its original number. But you don't have to take the floor. I don't know. It's up to you. Some people don't. They're like, but isn't it more accurate this way? I guess so. But I don't know how much more information it really gives me. I like doing the floor just as a, just so I know, is it like error of 100 or error of 0.01, 0.00001 or something? Cool. Yeah.
For the homework at the very last problem, where you're plotting a piecewise function.
Yeah. Okay.
My question is just in the formula, it picks the year 1970. Is that the correct year? Because it's copying very much the formula from the readings.
Yeah.
And I'm curious because it takes the same year for different data sets.
Mm-hmm.
Is it supposed to be 1970 or is it supposed to be a different year?
This one,
It doesn't really matter, you're just changing the formula.
Yeah, so the main exercise is that you're creating a piecewise linear fit, but it's continuous, at least like C0 continuity. The derivative is not continuous, but the function is. So if you look at the 1970 and you're like, that can't be right, Professor Cooper's lost his mind, I'm like, it's totally fine to choose a different year. This was giving like an example of like if you're gonna do it, because the main thing, usually the missing piece is like that t minus 1970. Because if you just try to do a heavy side function with times t, it looks like the slope doesn't change. And we can try that out. So we got our NG by region again. Do I have pandas yet? Panadas? Yeah. I think it's cool. So I've got like my data loaded in, at least for the US data. Throw some squares in there. Then I want to create a Z matrix. First one's going to be time. Then I want like a whole bunch of ones, like just a column to say like some intercept. And then I want to say t minus, let's call it like split. t minus split times t more than equal to split. Because a true statement is going to be a 1, so it just passes on the t minus split. And a false statement is going to be a 0, so then it just plugs in a 0. Oh, and let's print out that z. And then I like to look at matrices to see, like, am I losing my mind? Am I doing everything right? And here it seems like it's doing what I wanted it to. First column is just exactly the year that it was. Next column is a whole bunch of 1s, which is exactly what I wanted. So I have some kind of, I'm solving for some offset, like the intercept. And then the last column is not at all what I wanted. So I'm glad I printed it out because it's 0s and then a bunch of 1s. So I did something wrong, right? Because I have to remember order of operations. Right now I'm taking t minus split times t and checking, is that more than or equal to split? So let's do the comparison before multiplying by t. So just put some parentheses there. And now I get more what I wanted. So it's coming up. 1971 is 1, then 2, then 3. So it's t minus, so the year minus 1970 in the last column. Now we're making progress. Because I can say and then EUS. So now I'm taking, in order to evaluate it, since I already made like the function, I already split the function into z and the coefficients. If I want to look at what the line looks like, I can take that z and multiply by that answer, that least squares regression solution for that, for those coefficients. So z at CUS. Yeah.
My question now, the last part of this asks for a prediction, past the data points that are there.
Yeah.
So essentially we now know the coefficients to this function.
Mm-hmm.
When we're plugging in that, how does the Heaviside function factor in? Because do you just drop it when you start plugging in the terms? Because it's a times t plus b plus c times t minus whatever that year is, but then it's also multiplied by the Heaviside function.
Yeah. So
do you just drop that Heaviside term when solving for a year past that split point?
Yeah. So like if I'm trying to find the prediction for 2025, then it's going to be 2025 times this value plus this value. Well, I guess just minus that value. Minus that plus 2025 minus, and then that Heaviside we can say is 1 since it's either a 0 or a 1. Like if we want to include it, but that's when I plug in that Heaviside, it is 1.
So mathematically, the Heaviside function either comes out to 0 or 1 depending on if the condition is satisfied.
Yeah, exactly.
Okay.
And then times this last value.
Okay, so essentially that third term drops out of the equation before that split point, mathematically.
Yeah. Yep. So if we were trying to like take this and
Trying to
go backwards, like how much energy did we use in 1950? Then we would have a 0 in that last term, and we would just use these first two values.
Yep. That makes sense. Thank you.
Yeah. And I went through this and said, like, all right, I can make that split at any point in time. So, like, all right, well, 1984, Professor Cooper was born, so that's got to be the most important split. And, like, it doesn't really change. It's not like damning evidence that, like, Professor Cooper changed the world as he was brought into being. But maybe when he was 16, that's when the world changed. So in the year 2000, maybe that's when the split should have happened. It's like, yeah, so when Professor Cooper turned 16 and started driving, that's when our energy use really started to decrease. So that's the true story. Is we should have split this in the year 2000. Or maybe two splits, 1984 and 2000. Because we can make as many splits as we want. Yeah, I don't know. 1984 doesn't seem to be like a great year to say like this is when things changed. There was something weird going on because it is like dropping, but it doesn't seem to fit the data much better to say that it was like 1984. Yeah.
Explain again what that red line.
What it means?
Yeah, as like as you change it, is it like your your projection is like being split into two? Just having a little bit of
Yeah, so let's undo all that ridiculousness here. Put this back to so like coming back to our original here, let's do this. Copy this one. And then we want those coefficients. So like this first coefficient, that one's describing just the slope before the split. Because the function that I'm trying to fit is that energy as a function of year is some slope times the year plus an intercept, and then plus like a new slope times year minus 1970, like some offset. Like I want to say that in 1970 the slope either increased or decreased by a certain amount. So that's where so this second value here is saying that this slope is 9.23 E2 minus 7.44 E2. So maybe 2 point something. So like thanks a lot, after 1970, the rate of energy consumption dropped by 7 terawatt hours per year. So we were using less, at least based on this least squares regression. It's not that that is what happened, because what really happened is it jumped up and down. But on average, if we kind of take best approximation of a straight line for those years, that's what we can kind of roughly say happened. Is that what you're asking, or were you asking different? Sorry, and I know we are wrapping up, so I don't want to keep you, but thanks for joining.
And then the second, like, value there is the B. Okay.
Yeah, and B is kind of like a nonsense number because it's telling you how much energy was used in the year 0, but that's way outside of our like extrapolation term. Because in the year 0, I don't think we were putting 1.8 million terawatt hours of energy into the earth. All right, thanks a lot. You too.